My name is Dmitri. I have a talk with a very exploitative name. I think when you apply for a conference, you want to do it on something like design patterns, because if somebody says no, then, well, how can you be against design patterns? It's universal. And for some reason, they still haven't died out as a phenomenon or been rewritten by Design Patterns 2.0. In fact, the original authors of the book, when they were asked if they, well, I think it was 15 years after publication, if they would change anything, they only said they'd throw out the singleton and keep everything as is. So, obviously I'm not going to cover like every single pattern, or indeed, try to replicate what people have already done in literature. Instead, this talk is basically a couple of examples of possible approaches. I'm not gonna try to show perfect code. Everything is going to be, public accessibility and whatnot. But it's mainly ideas. I am looking for feedback and criticism. I am doing some video courses on C++ design patterns, and it's exploration, because to be honest, I mean, if you look at the languages that came after C++, a lot of them, they essentially started to internalize certain patterns, in the sense that, for example, you have something like C#, which would just take the observer pattern and make it part of the language. And C++ hasn't gone this route. So that's another kind of note on the exploitativeness of the talk, because I'm talking about modern C++, but even modern C++ hasn't really internalized any patterns as part of language features. It certainly made our life a bit easier, but it hasn't gone so far as to, introduce new pieces of syntax. So some of the things I'm going to talk about are adapter, composite, specification pattern, talk about fluent builders, and even a functional design pattern. And let's actually jump in. Now, personally, in addition to C++, I do plenty of .NET development. And as a result, I sometimes get annoyed because, well, some of the things which we take for granted in other languages are not available in C++, and you end up kind of jumping through hoops to get it in a way. So a typical example is the SteelString interface, because essentially, let's suppose you have a string like this. Let's suppose then that you maybe want to separate it into separate words. So the trouble with that is that in most Java or .NET kind of libraries, you just do string.split, and you expect to find it there. Unfortunately, this isn't available in STL. At least I don't think it is. However, it is available in Boost. And the problem with Boost is that, well, the main problem, even though, yeah, we do have the functionality, the main problem is discoverability. I mean, how do you know that this function exists? Because if you type s.split, for example, you're not going to get anything. And in actual fact, since I work for JetBrains, we make developer tools, I was actually talking to my colleagues about, well, what if we pretend that any global function which takes a string is part of the interface? We can rewrite the code later on. Why not just show it in code completion? Unfortunately, this particular example is specifically designed to show that this is actually difficult, if not impossible, because the string here happens to be the second argument and not the first. So now you're saying, well, are you going to show globals, all the global functions which take a string at any location, which is unfortunately infeasible, and I don't know how big the actual list of code completion elements would be. And in addition, of course, if you were in any other language, you wouldn't really expect anyone to pre-declare the vector of strings before actually calling the function. So that's another thing that is very specific. And personally, the reason why I'm talking about adapters is because personally, I would want to wrap this somehow. So I would hide the string, and I would also hide some of this extra functionality. So I would prefer just auto parts equals s.split. And it should also work, for example, if I have lots of spaces in between. So I want to make a few default assumptions about how we're going to split the string. So if there's lots of spaces, I don't want empty strings inside the vector. So that's some of my own personal stuff. Now you might say, well, okay, just inherit. Just inherit from SteelString, and that's it. However, I do have some further annoyances or, well, not grievances, but just things which are objectionable. Like, for example, if you take somebody who hasn't done C++ for a long time, and you tell them that a string has both a size and a length, what are they going to think, typically? I think many people would assume that length is, in fact, the number of characters, whereas size is maybe the number of bytes that you've taken up, which is not what's really happening. So that's the reason, at least for me, for not inheriting from string, because I want to maybe not expose size, or maybe not expose some of the other internal members, and only have the interface that I want, which is what the adapter is all about. It's actually, you're given some interface and you're adapting it to some other interface. We've come from Russia, and we hit it every time we come to England because these things. I better not unplug any, but essentially, anytime you come to the hotel and then you're like, oh my God, I forgot it once again. And so this is a good illustration of what you encounter essentially. So here, what I'm saying is, okay, I'm not going to rewrite SteelString. That's really suicidal. But I do want my own embellishments on top, and I do want to somehow construct just a very simple adapter, maybe something that just has a string inside it. So we're not inheriting, we're just taking a string and storing it. But then what we can do is we can implement this as a member function. So a consequence of that is that you have it as part of code completion. It's discoverable, because discoverability, I mean, Boost is fantastic. And in actual fact, Boost is doing the right thing, because we have something called the OpenClosed Principle. So the OpenClosed Principle, basically, it says that things should be open for extension but closed for modification, meaning you shouldn't jump into your existing code, which has already been written, it's already been tested. You shouldn't jump into it and start modifying. So here, I'm not saying, oh, okay, let's do our own STL now. Let's give me the string class. I'll throw out all the extras. I'll put in the stuff I want. I probably wouldn't be able to do it anyway. I'm just not qualified to dig this deep in the STL. So Boost is doing exactly the same thing. It's saying, well, if you want to split strings, I'll give you a global function which can do exactly that. Unfortunately, in C++, as you very well know, we cannot overload the dot operator. We don't have this idea of extension functions or extension methods which we can attach, although I am cautiously enthusiastic about different approaches. Unfortunately, with C++, the way that it's going right now, it's not going to be as smooth as in C#, for example. And I've had arguments with people about, because some people think that you don't need this kind of function. You don't need to have extension functions in C++, but it's not just a concept which already exists in other languages. It's a validated concept. It's something that people have shown to work really well in all sorts of scenarios. But anyways, this is what we're stuck with. So we get an adapter which does a few things that we want. And then, for example, if you want the length, then you can just implement it once again as a member function. And I should explain why there is a get in front of the length here. And this is another, I guess, kind of a quasi-religious point, in that a lot of people, when they see something that deviates from standard C++, they say, this is by definition evil. If you're writing code which doesn't conform to the standard, and I think I have plenty of slides around which would actually not compile on something like GCC. But if you don't conform to the standard, then you're the enemy, and it doesn't really matter if you know for a fact that on your compiler everything works. So I can do stuff like this, and I don't feel particular guilt about it because it works for me, even though for those of you who don't know what's going on here, I'm going to explain. So essentially, some compilers, and I think it started in the Microsoft compiler, but it ended up being supported in other compilers as well. They've added certain extensions to make life better. So we have properties in C#, for example. We don't have them in Java. We don't have them in C++. In C++, you can sort of hackishly get a construct which exposes a pair of, well, in this case, a getter, but a pair of get and set functions as a property that you address like you address a field. And so it is a bit of a contentious point, because essentially, personally, I know that if I'm writing code for the Microsoft and the Intel compilers, I'm OK with it. And as a result, I can get this improvement in the interface, and that's why it's get length and not simply length. So the end result is that I can do stuff like this. So I can get my string, I can get the length, and if you look at the code completion listing, then size is not part of it because I didn't inherit from anything. I also have my split member function. So this certainly constrains string to a subset of the things that it was originally designed to do. But on the other hand, maybe that's OK for me. Maybe that's all that I'm doing with strings. And that's something that, in actual fact, I was just telling you about extension functions and how they would be nice in theory. Unfortunately, extension functions are, in practice, what they do is they cause a ridiculous amount of pollution in the completion listings, at least in other languages. Because essentially, as soon as you get extension functions, you're probably going to want to have them in a sort of template form, in which case you just have type name t, and then you have an extension function on that t. Or maybe you'll do an extension function on primitive types. And as a result, this completion list can just explode, because every library that you connect to, it will provide you some set of extensions. So it's a bit of a trade-off. But with adapters, you get exactly what you want out of what you're given initially. All right. So typically, an adapter is just something that would aggregate something or keep a reference to some object, and then you can actually aggregate multiple objects if you want to. So you might have a string, and you might also have some formatting for that string, like indentation if you're outputting code, for example. And then you can replicate just the APIs that you want, or you can alter their behavior in actual fact, so long as you're not passing this into any function which actually takes a string, because then you're in trouble because it's not a string. So you're actually you can pass its internals. We do it every day because string.c_str. Anytime you need a C-style string, you're already using that effectively. So it would be a similar idea in a way, but in this case, you replicate the APIs that you want, and you can alter their behavior however you want. And you can miss out the APIs that you don't need or that you find confusing, or even if you know how they work, maybe your developers would find it confusing. And I don't think that the tax on building such an adapter is very high as opposed to just using an ordinary STL string. So add your own features and customize it however you want. All right, let's try another example with the composite. Now, it's a bit of a strange design pattern because essentially, well, we know objects are, if you're using composition and you have member variables of other types, well, that's it. You're making a composite. However, it's really all about iteration. How do you traverse a complicated object? So I picked a scenario which is kind of relevant to today's popularity, I guess, because nowadays it's all about machine learning and stuff. Machine learning, as you may or may not know, is just a glorified kind of 2.0 version of neural networks. Well, not only neural networks, but it's in there. So the scenario is as follows. You have this artificial neural network. You have these little circles. They represent the neurons, and they can sort of connect to one another. But you also have layers. So you might want to sort of manufacture a whole chunk of them at the same time. And this is great, making a collection full of these neurons. But then you want the two ideas, the two concepts to be connectable. So you have, well, speaking mathematically, you have a scalar and a vector. And you want to connect a scalar to a vector, or a vector to a vector, vector to a scalar, whatever. And so in practice, a neuron might look like this. So it's just a vector with a vector of pointers for the incoming connections, outgoing connections, maybe some other extra stuff. And then you have the layer. And here we may as well inherit from vector. No harm in it, really. This dash dash greater than was supposed to be a curious arrow which would evoke some element of surprise. The problem is that since we make developer tools, we have this part of IDE called the formatter, and the formatter knows better than you. So when you write dash dash greater than, it kind of rips it apart. But anyway, so here is a layer. You specify the count, and it just adds a couple of neurons to the layer, and then you get the space explosion of trying to connect these things, because, well, you know that you can connect one neuron to another. That's very simple. You update the pointers on both sides. That works. However, you actually, in practice, if you think about it, you need 4 functions, because it's, two different types of objects, a 2x2 scenario, and they're different types. They don't inherit from one another. They're not both vectors of neurons or anything like that. So that is a good illustration of, well, one of the good illustrations of the composite design pattern. Now, I'm going to make a pause here and talk about what happens in C++ versus other languages. So in C++, there's really no generalization. There is no interface that you have to satisfy in order to present your object as a provider of things, in the sense that we do have the begin and end pairing, but that's kind of like duck typing. So this begin and end, it doesn't come from some base class with pure virtual members that you have to inherit. You write it, and it magically works. And the consequence is that we may want to have just a single function for doing all of these 4 operations. And certainly in other programming languages, it would work just fine. But in C++, it's a bit more weird, shall we say. So the kind of cop-out solution is to treat scalars as vectors of size 1. You can certainly do that. And it's not strictly correct to do such a thing, and you're obviously paying some performance price on doing that. But in addition, you might have different topologies. You might have a ring or something, and you haven't taken that into account. You've now made the assumption that everything is going to inherit from a vector, which is, well, may or may not be correct, shall we say. So an alternative to that, and it's a really strange alternative, is exposing a scalar as in a kind of iterable fashion. So if you think about somebody using a range-based for loop, how do you feed a scalar value, just a single value, as opposed to a vector or some sort of collection? How do you feed it in an iterable fashion? It's actually doable. It's not really that hard, because, well, yes, other programming languages, they're more serious, I guess, about it, because you have specific interfaces. You have a specific kind of generic interface that you would implement if you are producing certain values. And you also have the yield keyword to kind of do it out of sync, I guess that's how you'd call it. So essentially, C++, it does duck typing. It basically says, well, if you've got a begin and end pair, I can try to work with it. I'll basically try to iterate it however it works. So we have, we can at least start on implementing this whole thing. So first of all, we have a neuron. We want to connect it to another neuron. We've already done that. But now I'm saying that, well, in addition to that, we're also going to have a more templated version, where for some other element, which is supposedly iterable, meaning that we can stick it in a range-based for loop, we can actually use this specialization. And by the way, this kind of construct is probably only compilable in Microsoft Visual Studio, because you cannot really stick specializations like this inside the body of a class or struct. But Visual Studio lets me get away with lots of insane things, so I just copied that over. So anyways, this solution is almost complete, but not quite, because it still makes the assumption that, well, in this case, a neuron can connect to anything which is a collection. However, and it can also connect to another neuron, so that's okay. The only corner case which we haven't covered is what happens if you have an entire layer connecting to a single neuron. That's not represented here because, well, it has to be somewhere else. So we really want something like this to work. So we want some sort of connect to, which iterates first object, whether it's scalar or vector, iterates the second collection, whether it's scalar or vector, and then just does the connect to, which is the specialization. Only problem is that if other is a neuron, then somebody is going to be calling begin and end on your scalar object, and I give you this. So this is really a silly way of treating the problem. But it does work, amazingly enough, because remember, the interface is quite dumb. It's just, it's going to take your begin, it's going to increase the iterator, and that's it. It's going to compare it against 10. So this actually works. This actually lets you connect any type of object. So the API usage would be something like this. Whether you have a neuron or a neuron layer, you call the connect2 function. And so if it's like neuron to neuron, you're calling the specialization. If it's not, then you have those range-based for loops, and they will actually connect the elements together, and they're going to be just fine. All right, let's jump to something else. This isn't a gang of 4, but it's also reasonably popular. And I already mentioned the OpenClosed principle, and we're going to see it once again. So essentially, the OpenClosed principle, as I said, you have an interface which is open for extension, meaning that you can build another hierarchies, you can inherit things, you can sort of override virtual functions, but you cannot go into the existing code that you've written and start rewriting it, or you cannot take your entire hierarchy and say, well, let's just add another base class to it. Because, well, you might be able to get away with it, and to some extent, we do provide tools to help you do it, but it's not the best way to go. So closed form modification basically means that modifying existing stuff is, it basically implies that you have to retest all of it and rethink whether your tests are actually valid, that sort of thing. So jumping into old code and modifying is bad, but good is making things initially generic enough so that they can be externally extensible, meaning that either somebody can inherit from some class or implement some interface, something to that effect, or they can maybe plug in on the side. And here's a very simple example. Let's suppose you have a collection of products. So you have, let's say, you have a product with a name, you have a color, and you have a size. And then you want to implement some sort of basic filtering mechanism for actually finding elements, like finding them by color, for example. And I know that in the C++ world, many people would immediately jump and say, well, why don't you just take an std function, and that can be a predicate, and you can just specify what you're filtering by. Well, no. There are many reasons why you might not want to do this. And specifically, well, one reason is it might depend on the kind of data that you're filtering for. Like, for example, if you're searching for strings, you might be doing it one way. If you're searching for some numeric stuff, you might be doing it on the GPU. That's one reason why you might want to just have an explicit function. Another function is maybe you just want to communicate intent. You're saying, you can filter my products by color, you can filter my products by size, but you cannot filter them by name, for instance. So essentially, if you continue this train of thought of having a function which filters by color, and then you end up with a function that filters by size, and then somebody comes to you and say, well, these are great, how do I combine them? And you end up doing a sort of by color and size. You once again have a state space explosion, effectively. Because you can imagine we have 2 criteria. If we had 10 criteria, this would be completely unsustainable. So you want to implement this. On the one hand, you want to implement it in such a way that you don't end up with a type name func somewhere, or a type name predicate in front of some general purpose function, so that you have some discoverability of what kind of filtering you support. But on the other hand, you want to make it kind of extensible, so that if somebody wants to filter by color or size, they don't have to physically open up the file where you've got the product filter already defined, and they don't have to add another function to that. So how can we do it? Well, we do it by, so essentially, yes, what was I saying? So this kind of approach is essentially breaking OCP, because you keep having to rewrite stuff that you've already done. And it assumes that it's even possible. It assumes that you've actually got access to the source code. And this is problematic. If this is a library that you've shipped to somebody, you cannot simply, you can't simply just change it like that. So it's really not flexible enough, because the more criteria you have, the more possibilities you have for searching stuff. And so filtering if you have just 2 elements, so filtering by x or y, or x and y, that requires 3 functions, or 4 functions if you have x or y together. And more complexity is difficult to deal with. So the specification pattern kind of tries to untangle that by essentially removing some of the core ideas and having them as separate. You'll notice then they're not template functions being fed into something. They're actual objects, their structures or classes. One advantage of such an approach is that later on, when you want to find out what kind of specifications you have in your project, you can just search for descendants of iSpecification. Tool support, it's great sometimes. So essentially what we've done is we've kind of ripped apart the construct that we have, in the sense that we have this very general idea of a specification, i.e. Some sort of functor which well, not strictly a functor, but some sort of object which determines whether a particular item, and you'll notice that it's actually type named T here, so it can be absolutely anything. It doesn't have to be a product, like we had a product previously. It can be anything, whether an item satisfies a particular constraint. And then we have this idea of a filter. And what the filter does is it takes both a set of items and a specification. So it basically kind of embodies the idea of filtering without putting any additional constraints on top of that. It's not saying I only filter products, or it's not saying I only filter products by color. It's not doing any of that. It's being as generic and as general purpose as possible. And so essentially what we end up with as we implement a product filter, for example, is we say this is an I filter of products. And then we implement the filter function, and we take the set of items, just a vector of pointers, for example, and we take a specification. And then for each of the elements that you see here, we just check if the specification is satisfied. If it's satisfied, we add the correct element to the collection, and we return that. So now making specifications. So for example, if you have a color specification, that would be represented by a separate object. And as I said before, yes, there is an alternative reality within which all of these are STD functions, and they're fed as template parameters maybe. But that reality is a lot more painful, especially if you have a kind of inhomogeneous search procedure for whatever elements you're searching for. So in this setup, we have a color specification. It's an I specification for a product. So that's once again where the actual item type comes in. And then we say, well, let's have a color that we're searching for in the constructor. And then all we have to do is satisfy the interface. We have to do this isSatisfied thing, which tells us whether the item is of a particular color. And you have a similar thing for size specification. So so yeah, let's first of all take a look at how that's actually used. So you have a couple of objects like an apple, a tree, and a house. They all have different name, different size, different color, and then you have a vector of stuff that you're looking for. So now the search is a bit more complicated. None of these calls, the filter call isn't a static function anymore. So we make a filter, we make a specification, and then we filter, providing the elements that we're searching for, as well as the specification. And this works just fine, and it only really leaves one question mark over it. What about the combination? Like if you want red big objects, for example, how do you combine the color specification and the size specification? And that's also really easy because, well, we certainly don't want to start making composite specifications like this, because this is once again an explosion of the number of classes, and it's completely pointless. So instead, we make combinators. We essentially have these abstract notions of a specification which combines two other specifications, because, well, nobody says we cannot do this. So essentially, you would have something like an AND specification, which is also a specification, so it satisfies the specification interface. However, in the constructor, instead of taking a constraint like size or color, for example, it takes two different specifications and it just checks them together. So its actual implementation is here in isSatisfied. You'll see that there is a double ampersand between the calls to the kind of first specification and the left ones and the second. So you check the first one, you check the second one, and then you combine them together and you make sure that they're actually functional. And as a result, yes, it does cause the API of the invocation to be a bit more convoluted, because you have to make a product filter, you have to make a color specification, you have to make a size specification, you have to make the AND specification. If you want something green and big, then you specify both of the specifications for the color and the size, and then you use it in your filter call. So this kind of highlights the trade-off of patterns generally. And I think that sometimes, especially on Twitter, you see people talking about, I had a problem, so I used Java or something. Now I have a problem factory. That's actually a shot against patterns, not against the language, because patterns do require you to maybe write a bit more code. But the end result of what we've just constructed is that once you've got these core building blocks, like I specification, for example, you don't have to touch them anymore, ever, because they're OK. It's an interface which checks a single object, whether it satisfies a certain criteria or not. That's really it. And from then on, what you're doing is you're basically using inheritance to make sure that additional definitions which relate to your business needs, relate to maybe what your boss told you we should or should not be filtering by, those are reflected in the descendant classes. All right, so the simple filtering solution that we had at the beginning is tough to maintain. It breaks OpenClosed Principle, and it's not really flexible enough. So we abstract away things, and that's something that patterns generally do. They abstract certain notions. So the notion of satisfaction of a criteria can be abstracted in a separate type, and then you abstract away certain other concepts, like, for example, the idea of filtering. That's something that you have a set of input items, and some of those items end up as the output. That's the concept of filtering. So you take that out, and then if you need to have some sort of mishmash of, for example, specifications, then you can create additional types which are living side by side with what you've already got, which combine them and which let you do those slightly more complicated operations. All right, let's take a look at yet another thing, which is Groovy style builders. I don't know if you've seen Groovy style builders, but essentially it's all about this idea of building DSLs inside whatever programming language. And many new programming languages nowadays, when they come out and they show that, oh, look, if you're using our language, we've made it easy to construct a web page, for example, and that web page looks, the HTML looks almost, like proper HTML, but it's completely valid. It's a set of completely valid constructs in our programming language. So, so this is a good scenario to take a look at. So if you think of a set of structured data like an HTML page, it's structured, it's formalized, you know what it consists of. You can define a couple of rules, like a paragraph cannot be in another paragraph in a web page. And the question is, if you're giving somebody an API for building web pages, let's say you're making a web framework, can you actually make an API which comes as close as possible to this notion? And the first start would typically be ugly. If you want to make a list of the items hello and world, you would just make a O-string stream, dump the data in there quickly, print it, and you're done. However, it's not particularly user-friendly because, well, it's, if you want to make any changes, if you want to change the set of list items to, I don't know, a set of paragraphs, you would be fiddling with strings, basically. So as always, you end up turning it into an object-oriented notation. You define this idea of an HTML element, meaning a tag. It has a name, it has text, it has maybe some sub-elements as a vector. You might have some indentation or something, and you have, well, in this example, you have a pretty printing function which does all the nice layout and whatnot and outputs that. So a kind of, before we get to the really nice-looking stuff, you can construct a builder pattern. So essentially kind of a separate object which helps you construct all these wonderful things. Because essentially, you can start working with this API straight away. You make your root element, then you take its elements collection, you add some more elements, but at some point you just want some more help, shall we say. You want something like an add child function. You just say, oh, I'm going to have the name of the child is going to be li, list item, and the text is going to be hello or world, and then it will construct the inner element and add it to your current elements. Something like that. So it just makes life a bit easier, and the end result is that you've already got, you've simplified the construct somewhat. It's by no means perfect, but it's already, you know, it's improved compared to just constructing a string and putting it using stream output operators. So then what you can do is you can make a fluent interface, which means that instead of a void returning function, addChild actually returns reference to self, reference to, well, returns start is basically. So what this means is that if you're calling lots of these addChild constructs, you can string them on top of one another. So the end result is that you can say builder.addChild, addChild, and so on. Now this is just a cosmetic thing, but returning a reference to self is what makes the builder so-called fluent. And it's done in lots of APIs all over the place. So we can now proceed to improve upon this model by saying that, well, OK, it's great to have this separate HTML builder construct, but how do we associate between the builder and the thing that we're building, essentially? So what you can do is you can just grab the element that you're constructing, in this case, the top-level HTML element, and you can say, well, how about we give the user of this API some hint as to what can actually be done? So maybe we take the constructor to HTML element, we get rid of it, we hide it, whatever, make it private, and then we have this static build function. And that's the only way that, you know, you can at least begin constructing the object. So you have a build function which actually returns a builder, and that builder can, for example, take the name of whatever the root element is. So in this case, the syntax changes slightly because now you have the element that you're building in the first place, and you're calling the static build on it, and then you're using the fluent interface. So we've reduced the invocation of this construction of a list of 2 items to a single line of code, basically. Well, it's 2 lines here, but you get the idea. You'll probably do more indentation in the real world, but it's like one single fluent invocation. So I mentioned Groovy, and Groovy-style builders, they kind of take it one step further in the sense because they say, well, this thing at the bottom, it still doesn't look like a web page. It looks like a bunch of function calls. So can we make it even closer to reality? Can we somehow express the structure of the HTML that we're trying to construct directly in code? And this is actually something that's been made possible due to, well, initializer list, among other things, because we want to hide all the function calls. We want to have something like this. And surprisingly enough, you can get exactly this in C++. Or maybe not surprising, but anyways. Uniform initialization. You basically, we still have this idea of an element or a tag. And then this element, we just define a few more constructors. So you can define a constructor where you specify a name and a chunk of text, or a name and a bunch of children, for example. And the consequence of this is that you can then specialize. You can make your own rules. So we have a general purpose tag, and then we say, well, there's going to be something called a paragraph. And the paragraph, it uses P as the tag, and then you can sort of pass the text over, or it can grab and initialize a list, and that's going to be the children of the paragraph, like if you have something else inside a paragraph. Maybe you have some text plus an image, for example. So you can also have an image, which, once again, it's up to you what kind of constructors you make. So in this case, what we're doing with this constructor is we're essentially saying that you can only have an image with an address. You can't have an image with a paragraph inside it because it doesn't make sense in HTML. So in this case, what's really happening is you're constraining the API. You're saying that by virtue of providing only the API that I specify, I'm basically getting the user to do the right thing. Because if they try to put a paragraph inside an image, the program won't compile. There's no initializer list in here to stick some other tag into. There's only the URL. And the end result is roughly this. So I know it's not the same as HTML, but it gets us very close. It gets us very close, and provided you communicate it to the user correctly, it's a totally viable thing to use for building objects. It's kind of like a mini DSL, effectively. There's only one real problem with all of this. And that problem, once again, like in the start example that I had, is discoverability. So unless you've written documentation explaining the users explicitly that it is possible to use this particular notation, there is nothing inside the IDE or nothing inside the compiler, certainly, to actually tell them that this is a better way. So unless you've written some documentation for it, they're not going to know. They might start making an instance of P because, well, P is, you know, it's a class. You can make an instance of it. They'll make an instance of P called paragraph 1, and then they'll be saying paragraph 1 dot children dot pushback, making a new image, that sort of thing. So this kind of API is nice, but it's not. It's difficult to explain unless you've explicitly said that. Oh, by the way, you know, we support this wonderful way of this wonderful notation. All right, so then the whole thing with builders is actually really interesting. We already looked at the fact that you can make fluent calls. That's actually not restricted to builders. Just if you want an API where somebody puts a dot after the call and then does another call, just return star this, or if it's a pointer, then return this, and they can do a dash greater than and follow that on. But facet builders are another kind of complication, shall we say, of builder patterns. You know, like it's like in watches. We have simple watches, and then we have complications with lots of mechanical spindly bits. Similar idea. So essentially, you might have an HTML element, like an image, for example, and it might have lots of different aspects which are independently customizable. Like, for example, if you have an HTML image, that image, yes, it will have a URL to whatever image you're showing, but it will also have some metadata. It might have some inline CSS definitions. It might have even some JavaScript attached to it, or I don't know what. So the end result is that you want to customize different parts of it. Or you might have, well, in my trivial example, you might have a person, and that person might have some address information, and they might also have some employee information. So those builders, they might have their own specific logic for how you want to initialize an address. Like, for example, in England, for example, you can, in many online web forms, you can just type in your postcode and your house name, and the rest is inferred because the system knows how. So these kinds of rules can be embodied in different components. And you might have specific employment information, the way that you assign, and the constraints that are put on that. So essentially, we might want to have several different specialized components which are all involved in the construction of this person class. And the question is, well, how can we do it in a reasonably API-friendly way? You'll notice that a lot of what I'm doing here is not so much, it's mainly syntactic sugar in a way. It's helping the developer figure out how they're intended, how the designer intends them suggest that they should be working with code. So this idea of several builders goes something like this. So let's suppose we have a person. We have two different aspects or facets of that person that we want to build up independently, and we want to provide an API such that they can do it. So we don't allow them to just call the constructor and then start, you know, initializing the fields. Maybe we want to do it in a more civilized way. Or maybe we're doing some sort of, maybe we're enforcing some bizarre form of immutability. I don't know. So the end result is if we agree that we want to build up the address information and employment information separately, what we can do is we can do the following. So we can we can construct. I don't want to say we can build a builder. That's kind of strange. But we can construct a more complicated builder. And there's lots of stuff happening here. So essentially, this object is building up a person. That's what the top line is. That's what is being built up. However, it has different constructors. One of the constructors actually takes a reference, and another constructor assigns this reference to the object being built up. That might seem a bit complicated, and you'll see in a moment why we're actually doing all of this. And incidentally, yeah, I'm doing operator person at the end so that you can actually do some long invocation, and at the end result, if you have a person variable on the left, you'll actually have the assignment. But anyway, so we don't have just one builder doing everything. Instead, we have these member function called lives and works, and they're exposing sub-builders. So they're exposing different kind of facet builders for initializing the different aspects of a person's life, essentially. So if I jump here, these are the implementation of lives and works. And this should explain why we have that constructor which takes a reference. Because essentially, we're building up this person, but we're doing it inside separate builders, which are simply being returned out of here. And now we can take a look at what these builders actually do. So a person address builder, for example, it would allow you in a fluent fashion. You'll see that there is a self ampersand here, so it's being fluent, and it's allowing you to say that we have a person who lives. Remember, lives is the name of the function. So lives at, and then specify the address. And then after you specify the address, close the round bracket, you can put a dot and say with postcode and specify the postcode. And then say in and specify city. The only question which remains is, let's suppose you're building up an address. How do you jump from building up an address, which is a fluent function call, how do you jump from this to building up the employment information? Because remember, we're returning self here all the time. However, look at who we're inheriting from. So this sub-builder is actually inheriting from the original person builder. So it's not like person builder aggregates these builders and gives them out. Instead, it actually is. So the person address builder is in fact the person builder, which means that the person address builder also happens to have these two functions because it inherited them. And as a result, when you're done with specifying address information and you do a dot, instead of continuing with the address info, you can effectively say works and then specify the work part. So essentially for the job builder, it's a similar story. It's a similar kind of builder. So it inherits from person builder once again, and it has, so you say the person works at company name as a position, earning so-and-so. And if you put all of this together, well, we can't put all of this together yet. We have to make a few changes. So typically, you can hide the constructor of person and just make a static function call for creating a person. And then you have a couple of friend classes so that those builders can actually get into the person and fiddle with the private fields. And then you can do this. Now, I'm being very, well, I guess I'm cheating a little bit here because it's all nicely laid out. If you actually do it in a modern IDE and you put that semicolon in the end, it's not going to be ruined in terms of alignment, but at least you get this API. So you essentially you say person create, that gives you a person builder. You call lives, that gives you a person address builder. That person address builder can be used to build up the object. So you say at so-and-so with postcode in London. But at any point in time, even though you're in the address builder, you have an ability to call works because lives and works have been inherited. So you call works, that gives you a different builder, also working on that same object. That's the reason why we had the constructor assigning the reference. And you specify a few more. And towards the end of it, if you have person P on the left, we specified the conversion so that it's automatic. So you don't have to say something like dot as person at the right. So that's essentially how you can construct this kind of multi-part object construction mechanism. And once again, yes, it is more work. It is more work, and it's not that easy to realize why we're doing this kind of inheritance. But the end result is that whenever somebody actually, whenever you give this object to somebody, they can more or less guess the kind of sequence of steps that they have to do in order to initialize it. And of course, here I haven't been really explicit in terms of like you have to initialize the address before the employment information, but you can do it. Because essentially, this interface that I've exposed, it's a very malleable thing. You can have builders within builders. You can have builders inheriting different aspects of other builders. So these transitions from one sub-builder, I guess, to another, you can totally control how that happens. And of course, it really only makes sense if that's your goal. If your goal is to constrain somehow the API user to do things in a specific way. All right, so let's try something that is less OOP, because I'm gonna try and building a monad, which monads are just well, they're also design patterns, but they're from the functional side of things. And in C++, well, C++ isn't a kind of functionally specific language, but we do have function literals, we do have STD function, we do have lambdas, so we can we can maybe get away with some stuff to a certain degree. So one thing that I want to talk about is the presence and absence of particular data inside the class. And we certainly have lots of approaches to that. So if you, there are different ways of expressing the fact that a person has, let's say, a house name. That's a good example because like if you're like me, you probably have a house number and the street and so on. But if you're like Enya and you bought yourself a nice Scottish castle somewhere, you probably don't have like 123 London Road on it. It probably is just called whatever castle. So house name is something that I might not have, but somebody else might. And so if you want to somehow test for the presence and absence of such a value, there are different ways of actually expressing it. So one way is to simply, you know, if you're using something like a string, you can just say, well, let's have the whatever the default initialized value is. So if there is no house name, then string is just going to be an empty string. It's not, there is no special way to indicate that the string was not assigned ever. Another way is a pointer, obviously. So you have an LPTR if that hasn't been assigned. And then there are specific ways such as, well, we have uninitialized smart pointers, for example, or you have the more idiomatic approaches like boost optional. I guess is it already STD optional, or it might be at some point. Anyway, the point is that there are different ways of expressing this very simple construct. And once again, we're, well, with the last one, we do have some success in communicating the fact that something is optional, but it really might depend on the API. So monads, yeah, they're design patterns in functional programming, and they're kind of things that people construct out of the fact that they do have things like first-class function support and some of the related concepts which are not really functional programming, but they're kind of, they typically go hand in hand. And unfortunately, we don't have many of those, but we can try to implement something to a certain degree. So I've constructed a deliberately artificial scenario here where I've chosen pointers as my presence or absence indicator. So I'm basically saying that a person might have an address, or they might have a null pointer, and then an address may or may not have a house name, and I've chosen char star instead of string because, well, I like to cheat sometimes. So it works for an example. The end result is that, let's suppose you want to print the house name, if any. You end up writing something like this, because if you're getting through a chain, like you want to get the person, then their address, and their house name, you have to check that all of those parts are actually not null. And an unpleasant consequence of this is that you would write something like this, more or less. And that's just a, you know, if you have 3 levels of depth. If it's more, then it gets even worse. So the question is, how can we internalize the fact that throughout a certain set of steps, we're checking for null at each step? Is it possible to somehow make that implicit as opposed to explicit so that we don't have to write all of this? And the MaybeP monad tries to do exactly that. So this idea of drilling down into some data structures while behaving in a null-safe fashion, that's something that we try to implement in code. So what we're going to do is we're going to construct a MaybeT, which is just a temporary wrapper, but this wrapper has certain behavior for actually checking that whatever it is that we're doing is actually correct. And this wrapper is going to keep a context. So the context is going to be the pointer to the evaluated element. So as we drill into person, then address into name, we're going to keep that context, and we're going to be referring to make sure that it does actually point somewhere. So while the context is not null, while we're working with a valid usable object, we're OK. We can call functions on this object. We can do whatever we want with this object. We can drill down further into the depths of the object. However, as soon as we hit a null, propagation does not happen. Now, the chain of calls that you're going to do, you'll see that in a moment, that still does happen. You still call lots and lots of stuff, but they're all like no-op, essentially. I'll show you how that's done. In my implementation, it's all done using lambdas. So essentially, we can define these tiny little functions which let us go deeper and deeper into a an object, or it can perform some operation on the object, provided that the object is valid. So here's a construction of a maybe of t. So essentially, we just keep a pointer to the context. Unfortunately, well, at some point we are going to get this in C++. Unfortunately, at the moment, I end up making these, global functions which help us with type deduction, because you cannot just write you can't just make a new maybe of and feed it a person pointer. Type deduction won't work there. You would have to specify that it's a person. So I basically keep making these. Hopefully, at some point they'll fix the deduction, and we won't have to do this. But that's not just C++'s problem, by the way. Similar things in C#. Anyways, what's happening right now is that as we want to print a house name, we're getting a pointer to a person, and we construct a maybe, which is just a wrapper. So we're essentially setting the context. We're saying that we're just going to store this pointer, and we'll continue later on. So maybe of p is essentially a small factory function for a maybe wrapper. And then when you press the dot, you have an ability to explore the context of maybe, but explore it in a safe way, such that if p at this point is null, your program won't explode, because somebody internally is checking the context against null. So here's how it's done. So let's suppose that I want to define a function which gets called upon the context if and only if the context is not null. So here, unlike in a few examples ago when I was saying that I want to specifically avoid any situations where a function is a template parameter, here I'm actually OK with it. I'm saying that given that we have a maybe already constructed, we might want to call a function called with and pass it a function, which can be a lambda, which lets us do anything we want, like, for example, drill into the person, but only if it's not null. So if it's not null, then we call this line. Whatever the function is, whatever function we passed in, we call that function with a context, because the context is valid, and then we wrap it in another maybe. OK. However, there's only one piece of unpleasantness with this implementation. It works just fine if everything is not null. However, if it's null, it's very difficult to determine what type you should be returning, because I have auto here. So the problem here is that we have to get the type from the function somewhat. But there are a few more manipulations that are required for that. It's not as simple as that. So essentially, the question marks that I have here, they have to return. They also have to return a maybe. We cannot have different return types for the if and the else. And for the else, we're definitely returning a maybe, because, well, that's what we should have. So what is the set of question marks? So the type that we're returning, it should depend on the type of evaluator. It should depend on the return type of the function that we're getting. However, the evaluator, the function that we're using, actually, by our notation, by our design, it returns a pointer. And we just need an ordinary type parameter. We don't want the maybe of u. We don't want u to be a pointer. We just want it to be an ordinary object. So we end up doing something like this. And it's great that we're able to do this. It's not very readable, but we essentially get the decal type of the function if it were to be evaluated with a given context. We remove the pointer, and we construct a maybe out of that. So here, we're not using maybe with a small m to get sort of type deduction automatically, because it's an OPTR. Because we're saying that, well, if it's null, then we're going to cancel this entire. Well, we're not canceling the entire evaluation chain. We're neutering it. We're basically saying that if we've hit a null as part of invoking the monad, then that's it. We're not going to do anything anymore. And as a result, if I bring this up, the consequence is that every time that you call with, if you've got a broken object where there's a null pointer somewhere, nothing is going to happen, because we've internalized the very check. We're basically saying that if the context is null, we're going to give you another maybe, but it's going to be a maybe initialized with null PTR. Therefore, on any subsequent call, it's not really going to do anything. It will give you another maybe, but that's pretty much it. The only case when evaluation will actually happen if it's not null. Then you do call the evaluation on the context, and then you wrap it and you return it. So what does it look like? It looks something like this. So essentially, we grab a maybe of p, and then we say, well, on the first call of with, the argument is actually going to be the person pointer. So we can try following the person to the address. And this lambda, this lambda that we're passing in, will only be invoked if p itself is not null. If p is null, that will never be invoked, and therefore we're OK. And the same goes for the subsequent call. If the address is not null, then yeah, we're going to try getting the house name. However, if the address is null, there is no problem, because this lambda will be passed in, but it will never be called. And so we can build this chain quite deeply. One scenario in the real world where we have things like this is when you try to analyze code. So let's suppose that you want to write a rule for some variable declared in a function, or something to that effect. You want to say that if the function satisfies certain criteria, then we can factor it out or promote it to a parameter or something. Then you have to have lots and lots of these checks. However, your code model might be different. You might have a variable, but it might not be in a function. You might be inside something else. You might be in a class, for example. And so as you traverse any kind of construct, you basically internalize certain checks. And certainly in other languages where null is pervasive and used all over the place, you basically internalize these checks, and you have lots and lots of these calls. And also, as I mentioned, in other languages where you do have the concept of extension functions, these things don't really have to exist as part of a maybe. So the maybe of t here is a completely artificial construct that only exists because there is no other way for us to kind of carry the context throughout the invocation chain. If there was some other way, we'd probably do it. Although I wouldn't want to drag it through all the lambda calls and return, let's say, because you could do it. You could say that we'll have lots of global functions which return not only the object, but also this maybe, or some context, or rather. But that would be even more unpleasant. Now, this isn't particularly great by itself. Plenty of languages, when you have x returning x dot something, they make you write it in a much more efficient way. The simplest way that you sometimes get is you can replace the entire lambda, for example. You can replace it with just curly brace it dot address curly brace. That's the best I've seen so far, without even the round brackets. We did it in our own language, so it is possible. But with C++, that's kind of the approximation. Now, the final thing that we should do here is maybe print the object, assuming that we reached it, assuming that it's not null on any of the kind of invocations. So in this case, we can define a simple function called do, which really performs some action so long as the context is not null. But in this case, there is actually no drilling down. There is no drilling into further objects. So instead of returning, some inferred type of the evaluator, we just return ourselves, basically. We keep the same maybe of t throughout the invocation. So let's see how it works. So if you print house name with a null PTR, that's fine because the context is null originally, and it continues to be null, and effectively nothing happens. The whole invocation chain is a null. There is no problem with it. If you make a person, but don't initialize it, and you print house name, then the context is person, but person's address is null. So henceforth, the context is null. Once again, nothing happens. If you initialize absolutely everything, then we go through each of the invocations. The context is never null, and we end up actually printing the name of the house. So, I mean, this example, I've used pointers and null PTR specifically, but you can replace it with some other idea, like boost option or something to that effect. You can get certain situations where it's reasonably safe to not worry about it. Like, for example, if you have a string, it's not null by default. In other languages, it is. In C++, it's just empty. Talking about the std string. So in this case, yeah, you do get some concessions. But generally, this example is not specific to null checks. And it actually exemplifies something different altogether. It exemplifies the idea of kind of implicit propagation of certain information, of certain characteristics that you want to carry throughout the entire invocation chain. And yes, separate objects, like the actual maybe struct, are required to carry this information over, because there is no other way for us to do so. Default initialized types are harder. Like, how do you know when a string has been initialized? Well, you don't really. If you check that its length is 0, you still don't know. Maybe somebody didn't initialize it. Maybe somebody deliberately wrote an empty string into it to indicate something or other. So harder to communicate. So monads are, well, they're tough because there are nicer ways of defining them. And certainly, but it's a bit of a trade-off in one hand, because remember, like, for example, capture lists. That's a luxury. You don't get this in other programming languages, at least the popular ones. So maybe we should be thankful for it. And once again, C++ does not have this idea of implicit. So there is, if you have a lambda which takes one argument, you don't have an implicit name for that argument. If you did, that would be much nicer. So that's pretty much it. And if you have any questions, feel free to shoot them. I'm currently doing a set of courses on Pluralsight on design patterns. So eventually, well, if some of the stuff is already there, some of the stuff will be there eventually. So you'll be able to see lots more examples. And I like criticism. So either here or here's my email and Twitter. Just let me know what you think. If you can do something better, that would be totally awesome as well. Thank you.